Okay, good afternoon, everybody. I'm Lei. Right now, I'm a data scientist at Walmart Labs. So I talk about adaptive user segmentation for recommendation. Before that, just a little bit of background about Walmart Labs. So Walmart acquired this Cosmix in 2011, and then founded this Walmart Labs. So later, it acquired a couple other startups, and right now, they are still very aggressively expanding and hiring. So why does Walmart want to acquire some startups? Some are focused on social media, some are focused on cloud computing. I think the basic reason is that they think that e-commerce is the next strategy move for them. And because right now, Walmart really need to catch up with Amazon. Otherwise, Walmart probably just become another Borders. And so for Walmart Labs, basically it's an R&D center for Walmart e-commerce. It helped to improve the traditional e-commerce and also trying to find out new solutions, like new types of e-commerce for Walmart. So there are a couple of efforts in the labs, for example, search and product categorization, demand generation, SEM, SEO, and customer targeting. And also some talking about how to do this smart pricing. Basically, you monitor all these competitors and trying to dynamically adjust your product price. And also there's some other social, mobile, local efforts. So as for today, I'll just focus on customer targeting and recommendation. So when talk about recommendation, actually, during the coffee break, I talked to a couple of people. And many of them are doing some kind of recommendation. If you look at all these companies in the Silicon Valley, probably half of them have some kind of recommendation. You recommend news articles, recommend movies, music, friends, jobs, products. So even you can consider ads and even search engine as some kind of recommendation as well. So at Walmart, then we need to recommend products for customers. And there are different types of channels. One is basically when a user visits Walmart.com, then you want to do this on-site personalization. And then we also have the email targeting trying to bring customer back to the website. Of course, when a customer shop at Walmart stores, then you hope that by having this recommendation, you can improve their in-store experience. And finally, we basically have some partners trying to show ads when a user basically looking at New York Times, you show these ads. Hopefully by talking to them, you can bring them back to Walmart to do some shopping. But in e-commerce, typically we have different business criteria. That's why, in here at Walmart, we have a workflow trying basically decompose into two stages. The first one is basically we get all these different types of user activities and product catalog information, user profiles, and also there's some team provide some a social trend, what kind of products right now is trending at Twitter, and also the weather information together. Then we figure out, okay, what are the possible products a user is likely to purchase in the near future. Then based on this candidate set, we typically have another process trying to do this refined optimization. So this can be refined. It has different criteria. It could be about trying to improve the diversity when you have a bag of products for recommendation, or you're trying to optimize for revenue or profit margins. But as for today, I just focus on the first part, basically trying to, okay, given all these different types of user activities, how can we find out this relevant set about what are the relevant products for this particular user? Okay, when we talk about recommendation, I guess everybody has already heard about this Netflix price competition. So, and since then, so basically recommendation, this collaborative filtering gained the momentum. And right now, the most commonly used method is matrix factorization. That's actually why we actually tried matrix factorization at the first place. The problem with this matrix factorization is basically we have the hundreds of millions of users, millions of products, it's not so, you can apply some like Mahat, basically doing this iterative process. But considering that right now we still have a medium-sized cluster, we don't want to tear down our cluster. So we have to come up with some solutions so that we can do this faster. So we tried actually Michael Mahoney this morning, he talked about some randomized algorithm. Actually, you can basically downsample your data set a little bit and run some randomized SVD. Then this way, you use this as initialization, can accelerate this process a lot. But of course, like in this e-commerce, actually, we found that it's not just one matrix. Typically, you have some user transactions, user search for certain products, and then they browse for certain pages. So you have all these different types of activities together, and these different types of activities are correlated with each other. So you cannot just simply focus on just one matrix. So we hope that we can somehow capture these correlations together. So what we tried is actually very simple, straightforward. We just build one matrix for each type of action, just combine them together, and run this matrix factorization. And it can capture some correlations, especially like for the page views with transactions. But we found that actually matrix factorization does not perform that good as we expect. Then we think that probably there's some problem about this model. So when we think about this matrix factorization or all these latent factor models, it's essentially trying to do certain sense of clustering effect. Suppose like the latent factor for product, basically trying to capture all those products are highly correlated with each other. So we found that in the latent factor, viewing certain, basically like suppose for one product, viewing TV pages and buying a TV, they're somehow captured in one latent factor. But actually when you think about in e-commerce, you can, before you make a transaction, you were very likely to browse different types of TV products. But once you make a transaction, you don't want to recommend the TV anymore. And if you somehow make a really good TV recommendation with big discounts, the users are really pissed off. So it seems that we have to go something beyond just similarity, you know? So this actually is different from other domains. Because like if you look at the movies, music, you watch a movie, you can always recommend some similar movie, it's okay. But for product, it's not the case. So there's some negative, basically some negative effect about these user transactions. Even though they are highly similar, but they somehow have a negative effect over these similar products. So I hope that we need to figure out some other model to capture this negative correlation effect. And another one is basically, if you look at these user actions, actually there's a temporal order really matters. You always want to recommend, like say, iPhone first, then recommend accessories. But if you just look at the similarity, okay, I recommend accessories, then user might just get confused. Why do you want to recommend accessories before I even make a purchase about iPhones? So that's why we think this matrix factorization probably is not a right way to model these user activities in this e-commerce field. So then we go back to alternative approaches. So one of the simplest one actually we come up with, basically, okay, you just look at, we consider user action as a Markov chain. So based on his last or recent actions, we're trying to figure out what are the products he's likely to buy. Then we compare this Markov model with some other approaches. For example, we have another baseline, basically, is just you look at user actions, then you figure out what are the categories he's most interested in. Then based on that, you can figure out what are the best-selling products in these categories. So then we compare this Markov model with this like a category-based targeting using some email traffic. Then we also segment users based on their recency. So here the x-axis basically represent what's their, like basically 1 week represents that a user has some activity within past 1 week. Then 1 month means within past 1 month. Then here the blue bars basically represent the Markov model. As you can see that for those recent active users, they are performing pretty well. But for the users who are not active recently, then you just recommend this best-selling product within their interest categories. It's performed much better than the Markov model. So we have this simple segment-based recommendation. So we basically segment users based on their recent, whether or not they are recently active. Then based on that, after this segmentation, we try different models. One is Markov model, another one is like a best-selling product in those categories. Then just one simple segmentation, the revenue is boosted by 10% in this email targeting. Then we're thinking about, okay, can we do better than just this? So we look at some other possible patterns, like trying to come up with some other ways to segment these users. Then the first one we look at is by looking at the recency of the user distribution. As you can see here, typically most users are recently active, then it's decreasing, more like a long tail distribution. But there are two spikes there. So as you can imagine, these are basically during Black Friday, so all these customers just shop at Walmart here. So we're thinking, okay, probably we can segment users based on like whether or not they just shop at the holiday season or some engaged or regular users. Then when you think about more, then you can basically, you can come up with all these different types of segmentation. You can segment user based on their gender, based on their location, based on income level, and also you can also segment user based on these product categories. And then after you do this segmentation, we need to come up with a model for each segment. So this, we end up with probably hundreds or thousands of different ways to segment users. So that's why we need a more scalable approach to segment users. So ideally, we hope that we can find some niche neighborhood for each individual user. Then what we tried is basically we use some supervised learning to guide this segmentation process. So what we tried is basically we look at a time window saying that a particular user purchased product P1 and P2, then this basically, we just consider each product as one class label here. Then you backtrack for all the possible activities as features for this particular user at this particular time, okay? Then we hope that we can use this label information to guide this, to determine which features are more important so that we can segment these users more properly. So we have some workflow. It's basically we aggregate all the different types of data. Then based on certain criteria, we generate this targeted information for users. Then for this particular user at that time point, we determine what are the proper features we can use. Then we build some supervised models. And after that, typically we have to do some model compression because we found that if you just use a raw model, typically for the scoring process, it takes a long time. So we typically specify the model and based on certain criteria. Then after that, you basically do scoring and have these recommendations. So talking about the target generation, so we believe that the product has some trend. Basically, like for new product coming, then that's why you have this user buying these new products. So we only focus on recently purchased products. Of course, this one would not capture those new products which somehow has no transactions. So actually, that one we'll deal with that in the second phase. So basically, we have some exploitation framework trying to figure out for new products what are the likely response for different users. But here, for supervised learning, we just focus on, at least for those products in the market, on the market, and then we figure out, we use that as class label information. Of course, for some products, there are very few number of transactions, so we basically will backtrack this time window longer in order to collect sufficient number of positive examples. Then for feature generation, actually, I think that's probably one of the most important part. So we construct some short-term intentions based on their recent purchase product. So this, for recent actions, we keep the product level features. Then we're also incorporating some recency, because when we look at the user's purchase gap, actually it's a long tail distribution. Most likely, if you purchase something or interact with this product page yesterday, you are very likely to buy it today. But as the time gap getting larger and larger, then the likelihood is just getting lower. So we basically use some exponential function to approximate that. Then besides these short-term intention features, we also have some long-term interest features. So basically, we use this product catalog to aggregate all these product level activities so that you can capture. By just looking at each user, you have a multinomial distribution about what kind of category he's interested in. Then we also have some other meta features. These are all the possible segmentation criteria we can come up with. So we have this time since last interaction, how active this user is in the past, and also all these user profiles, all these different types of features. Then the key part is about, then the remaining part is about trying to train the models. So if you look at the problem, basically it's you have hundreds of millions of instances, millions of features, and right now we even have another challenge is we have millions of labels. We're really in trouble. So basically, any method requiring iterative map reduce, basically, no, we won't do that. So we have to make some compromise. The first one we tried is we basically try a naive-based classifier. So actually, it's pretty simple. You just simple count and compute the conditional probability. But actually, we found that it's highly sensitive to the features generated, and it's also because the class imbalance and the naive-based model basically do not perform that well. Then we tried some discriminative classifiers, and so we tried this SVM or logistic regression. But here, because all these labels, if you look at the raw data, is coupled, but then in order to scale, we have to decouple all these different class. Basically, we train these one versus rest classifiers, and then you can do this parallel training across different machines. Then we also, in order to handle this high class imbalance, basically you have very few positive examples, but you have tons of negative examples. So what we tried, okay, we hope that we can downsample the negative examples, just such that each machine can train on a small sample data set to get the build a classifier for that. So that actually works pretty well. And the training itself, because each machine can do that training just in memory, so it's pretty fast. Most of the time is basically spent trying to swapping. Once you generate these training examples, it takes a long while to do the shuffling to ship to these different computer nodes. So we think that, okay, probably we don't want to have, because when you generate the training example, it's basically just duplicate. For this one, it's positive example. For the next one, probably it's negative examples. So we hope that we can somehow reduce this duplication process. And we think about, okay, rather than train a one versus rest classifier, we hope that we can have some model that can handle this multi-label feature very naturally. So we extend the decision tree to handle this multiple label classification. And then you can actually, you can just easily extend the impurity function so that you can handle this multi-label classification. You can stop early so that each leaf node, rather than maintain just one class label, you maintain a label distribution, class distribution. And then you combine with some undampable methods, such as a random forest. So it's basically just downsample and do the undampable. It's pretty straightforward. So here, actually, are some of the ongoing efforts we have been pushing. Unfortunately, I don't have so far, we don't have impressive number to show you. So just to quick summarize, I think for recommendation, many people here are doing recommendation. We really need efficient and scalable machine learning techniques. So here we use some supervised learning techniques for recommendation. But there's one question I have is basically how sensitive, because right now we use this downsampling and ensemble. I would wonder if you have big data, do you really need that big data? That's one question I have. Like how is your classification performance would change with respect to the number of training samples you get? So I would be happy to dive deeper into that. And another one is by right now, because you can see that this machine learning is just one component in the workflow. So it requires a long process for parameter tuning. So if we can somehow understand how much sample, whether we can do like a quick exploration using small samples, so that we can scale, we can just generalize to large data set. And another one is about the feature. I think I feel like this feature generation is more like an art rather than science. So I wish that someday we can have some automatic feature generation process. Okay, so last comment about this MapReduce and machine learning. I think because I look at like Graphlab, Spark, and also Giraffe, I think when we think about this large-scale machine learning, we're always saying that MapReduce is not that good. But when you look at all these industry companies, most of them, they already have MapReduce implemented. So rather than have one paradigm just specific focus on machine learning, we should think about that, whether or not we can work compatibly with MapReduce, because MapReduce, they are there, they still have some utility for some other functions. So I would just say, end with this quote from Lincoln, Abraham Lincoln, say that we need to figure out how to comply, how to be compatible with this MapReduce for large-scale machine learning. Thank you.